All right, folks, welcome back. We'll go ahead and get started. I feel like we need an OChem theme song or something like that to sort of play in the minute or two before class. But I'm not yet ready to deal with all of the licensing issues that would come from that. So, the exam. There's still some folks that have not yet taken the exam, and so I'm going to not talk about any specific problems on the exam right now. Once the folks that still have to take it have done so, I will make it possible for you to go into Learning Suite and see the items that you missed, what your responses were, what the correct answers were. I will also, like I did last time, produce a few videos for each question, walking you through it, and we'll make those available on YouTube. And let's see what else. And then some point later today or tomorrow, I will send out a link to a Google Sheet where you can sign up for one-on-one meetings, either in my office or via Zoom, if you want to talk about your specific situation. Overall, the average on the exam was like 78, and the median was 80-something, 82, 83. So this is actually really good overall. I'm pleased with your performance. It may be that what you have been doing to improve your study is working. It may also be that you're frustrated because it hasn't yet borne fruit. If you're in that situation, don't panic. There's still a lot of time left, and let's definitely talk about your process so that we can make it better. So yeah, stay tuned, and we'll talk. With that, we are now ready to begin preparation for next exam. Yay! Which always happens, and it's a never-ending stream of exams until you graduate, and then you don't ever have to do homework again if you don't want. But then, 20 years later, if you're like Amber, you might decide you want to go back, and then you have homework again. And it's sort of fun. I feel a guilty pleasure. I mean, I am trying to support her, as I said, and cook dinner and other things, and not that I want to imply that I'm doing anyone a favor by cooking dinner. All right, it's not like it was her job to begin with, and that. But it's what I'm saying is it's sometimes funny for me to not have any homework while she has homework. I sort of smile to myself because I know I'm making all of your lives terrible while someone else is making her life terrible. And I'm just standing around and reading a book, looking at my phone. There's going to be I better not rub it in too much. Let's see. I'm trying to decide whether to tell you. I'll save this story for later because we may need it another time. So today we're pulling back the curtain on all the complexities that have been happening in the background for SN2 and SN1 reactions, even though we haven't been talking about it. All right, and this has to do with the potential for elimination reactions. And the conflict between substitution and elimination reactions is basically an argument over whether a nucleophile or base attacks at the alpha carbon versus the beta proton. And so I'm going to explain what that means in a couple of different contexts. We're going to begin maybe with the most familiar one, the carbocations, because we've already talked about hyperconjugation and carbocation stability. And it turns out hyperconjugation is key to understanding why a nucleophile gets to choose in the first place whether to attack at the alpha carbon or the beta proton. So the example I'm going to draw here is one that you've seen already. I'm going to simplify this by just focusing in on one of those adjacent carbon-hydrogen bonds. The positively charged carbon is here. Using sort of a naming system that we talked about last time, the carbon with the positive charge will be hereafter designated alpha carbon, and the carbon adjacent to the alpha carbon will hereafter refer to as a beta carbon. The protons on the beta carbon we will call beta protons. As we've said before, hyperconjugation makes it so that the LUMO on that alpha carbon, which we've thought about as the empty p orbital, is delocalized and spread out onto the adjacent carbon-hydrogen bond. And if you do the calculations for what the LUMO looks like for this carbocation, I'm only showing you part of it, but actually it would equally extend to other carbon-hydrogen bonds. This is what you see. This is the LUMO of this carbocation. Now that's a bit more nuanced than we had thought before from identifying HOMO and LUMO. The LUMO is basically the minus combination of the carbon-hydrogen sigma from the beta carbon and the empty p orbital. And what it means is the LUMO spreads out onto the alpha carbon. I'm sorry, it's already on the alpha carbon, also spreads out onto the beta hydrogen. So that a nucleophile that's attacking the LUMO can choose, do I attack at the alpha carbon? If so, that gets me to a substitution product. And of course, since this is a carbocationic intermediate, that substitution product would be SN1. In contrast, if I'm a nucleophile or a base and I attack at the beta proton, that's going to lead me to elimination products, which, because it's happening from the carbocation after the leaving group leaves, we're going to call E1. All right, so let's talk briefly about the consequences of attack at one versus the other. Of course, we already know this from the for SN1. As a nucleophile comes in, we get end-on-end overlap. We get a new sigma bond between the nucleophile and the alpha carbon. And that product would look something like this. And we talked about stereochemical issues last time, which we won't repeat here, and you can go back there for further information. You can attack from above or below. Understanding what happens when you attack the beta proton is, I mean, you could just memorize it, but I've actually recently found it useful to think about it in a little bit different way. So remember that I said that the LUMO is the minus combination. I'm going to just recopy this and get rid of the substitution arrow. And I'll be general here. We're dealing with a nucleophile slash base. And that will attack the LUMO. If it attacks the LUMO at the beta hydrogen, seeing what happens next it's useful to think about not only the minus combination of sigma and P, but also the plus combination of sigma and P. We've drawn this before when we first talked about hyperconjugation, mentioning that hyperconjugation allows the electrons in that carbon-hydrogen bond on the beta carbon to spread out towards the alpha carbon. So that plus combination orbital sort of looks like this. And it's still mostly, those electrons are mostly between the beta carbon and the beta proton, but they're also delocalized a little bit in between the alpha carbon and the beta carbon. In fact, this sort of looks like a wannabe pi bond. like all it would take to be a pi bond is for those electrons to just shift over a little bit and be evenly shared between the two carbons. And that's possible if you get rid of the proton. So you attack at the proton, form a new, because you attack at the proton, you get end-on-end overlap between nucleophile and the proton. And then the electrons from the carbon-hydrogen bond shift over to form a new pi bond. Now, we're not going to draw the mechanism for this reaction in that way, really, ever again. This is just to illustrate that the electrons in the nucleophile are involved in the reaction because they attack the LUMO, and then the aftermath of that is that the electrons in the carbon-hydrogen bond shift over to form a new pi bond. So if we were to show this mechanism without any of the orbitals drawn and just in this sort of minimal level of detail, we would show a nucleophile versus base attacking the beta proton and the electrons forming a new carbon-carbon pi bond between alpha and beta carbons, and this would be the product of that reaction along with the nucleophile slash base having picked up a proton. All right. Question so far? Yeah. Would it be incorrect to say that the LUMO of this molecule is the empty p orbital? No, you can do that, but you're not going to get the prediction right if that's all you know. You also have to remember that because of hyperconjugation, some of that LUMO is on the adjacent hydrogen. We're looking at this now in a probably more technical level of detail than I would require on an exam, but I want you to know, I feel like the background is useful for understanding why the mechanism is the way it is. Other questions? Yeah?
What comes time to like determine whether it's going to go E1 or SN1? Is it determined, is it like random, or is it based off the nucleophile? Or?
It's a good question. I mean, when it comes time to decide between SN1 versus E1, can you tell which way it's going to go? And the answer to that is not really. So I'm going to pull over an energy diagram that we drew before, trying to remember where it might be. Ah, yes. A horrible energy diagram of, SN2 versus SN1. And now that we see that two different things can happen to that carbocationic intermediate, it maybe seems a little silly to call this the SN1 transition state, because that's just the transition state for the leaving group leaving to give you a carbocation. From that point on, the fate of what happens next to the carbocationic intermediate is going to depend on the relative heights of, we'll call this second barrier along the SN1 pathway. We'll call this maybe the SN1 transition state. This is, remember, along this axis, we're just breaking the carbon leaving group bond. On this axis, we're making the new carbon nucleophile bond, right? So leaving group leaves to get carbocation. In the SN1 pathway, nucleophile attacks the alpha carbon. So yeah, we could update this with now, if we go the other way, if instead the nucleophile attacks the beta hydrogen and we form a new pi bond between alpha and beta carbons, then we're talking about an E1 reaction. And instead of substitution products, we've got elimination products. And this points out something that your text actually holds off on until sort of the very end of chapter 8, which is they tell you that it's basically impossible to get selectivity between SN1 and E1. Once you get to that reactive carbocationic intermediate, you pass the rate determining step, and so there's very little control over which direction you go. So this is the E1 transition state versus the SN1 transition state. Even if their barrier heights are a little bit different, it's not going to be enough to make a huge difference. And so we're going to assume that SN1 and E1 always compete. It's a good question. The question here in class is, does that mean that it's always 50-50 between the two? No, it doesn't. The idea that they're going to compete with each other doesn't mean that we expect even distribution of products. We just expect the possibility of finding both products. The goal is to get to the point where if you were in the lab and you tried to do a reaction that required a carbocationic intermediate, you would not be surprised if you saw both substitution and elimination products. If you found an example where, hey, 90% of the time we got substitution products and that's good enough, we can purify it and what's left are elimination products, but we don't care, that's great, and that happens all the time. And on the other hand, if you try it and it's a mess and you've got a lot of both and you can't separate them, why then you'll know what happened. You won't be surprised. But on an exam, I would expect you to select all of the elimination products and all of the substitution products that could form from a given starting material. Yeah? Would having a big bulky nucleophile change whether it's SN1 versus E1? No, because steric issues are a lot less of a problem for an sp2 hybridized planar intermediate. The other thing is that presumably, Staten, you're talking about this particular base or some bulky base like that. We're going to see that strong bases and or strong nucleophiles are not going to wait around for the carbocation to leave unless they have to. And we're going to see that elimination reactions are always an option for tertiary alkyl halides. So this guy can't do SN2 reactions because it's too bulky, but it's not going to wait for SN1/E1. Instead, it's going to prefer an elimination reaction. We'll talk about that. We haven't quite got to that point yet. So we're going to assume there's basically not a lot of control over whether you go through SN1 versus E1. And for that reason, there are SN1 and E1 are not that synthetically useful. Now, why do we bother teaching them to you then? Well, because biology uses them quite a bit, and because it's a great chance to learn about carbocation stability, and carbocations are involved in a lot of other reactions. Okay, other questions? Okay, yeah. I'm sorry, the question is, what about tertiary or secondary carbocations? What about them? Yeah, we're going to see that the only carbocations that are good intermediates for these reactions are tertiary and secondary, but that will not provide, whether or not it's a tertiary or secondary carbocation, is not going to provide bias for going one way versus the other. Okay, others? All right. So we got a similar situation for the alkyl halide starting material for the SN2 reaction. So we're going to talk about that now, and let's just have this be a secondary alkyl bromide. Let's maybe put a methyl group there and a methyl group here. EIEIO. We've said before that for alkyl halides, the sigma star between the carbon and the bromine is the LUMO. But that's not the whole story. I want to show you briefly in the program Spartan what you see for what the LUMO is. If you draw this secondary alkyl halide, oops. Ah, yes, it's in the database. Here's the LUMO. Notice that it looks like pretty much the carbon-bromine sigma star, except some of the LUMO is on those beta protons. All right? Why is that? Well, it's because of hyperconjugation. So you'll notice, actually, we'll go back to Spartan, that if you look down the bond between the beta carbon and the alpha carbon, the hydrogens that have the LUMO on them are the ones that are lined up with that sigma star. So we can draw this on our own paper. Here is a representation of the sigma star associated with the carbon-bromine bond. You've got a node in between the two nuclei, which is how you can tell that it's an anti-bonding orbital. I'm going to fill in the colors that represent opposite wave function signs. And then we're going to remember the fact that we have a filled carbon-hydrogen sigma bond that can line up with and mix with the carbon-bromine sigma star. This is a chance for what we've called sigma to sigma star hyperconjugation between the adjacent CH bond and the carbon-bromine sigma star. And as we did before with the carbocation, when we mix a CH bond with a sigma star, you're going to get a lower energy plus combination and a higher energy minus combination. The lower energy one allows the electrons from the carbon-hydrogen bond to get lower in energy and spread out a little bit toward the alpha carbon, and the minus combination allows the LUMO to spread out onto the adjacent carbon-hydrogen bond. So what I'm hoping to show you here is just our representation of what we saw in the Spartan app. That is, we've got LUMO on alpha carbon and beta hydrogen. Much the same way as we did with the carbocation. The only difference is the key player on the alpha carbon is an anti-bonding orbital instead of a p orbital. Okay, is that sort of clear so far? Another important feature of this reaction is that not all of the beta protons have a lot of LUMO on them. You can get that actually from our calculation. See that the LUMO is really only on the beta protons that line up with the sigma star. And in fact, I'm going to turn off the orbital. The beta protons are only on the atoms that are anti to the leaving group. So we can actually illustrate this by doing a Newman projection. Let's just look down that bond between beta and alpha carbons. So in front is our beta carbon. The alpha is going to be in the back. From our perspective, this beta proton is the one that has some of the LUMO on it. And then we've got two other beta protons angled this way. The alpha carbon's in the back. Let's see, we would have the bromine coming out this direction, the other methyl group here, the other proton there. I can draw in the rest of that LUMO on the for the carbon-bromine bond in the back. And there's a lobe of that sigma star that overlaps with the carbon-hydrogen bond. Okay? So this is, and maybe I didn't want it to be that way. Hold on. Well, I want the blue to be in front. There we go. So the side-to-side overlap that generates these the new LUMO and the delocalized carbon-hydrogen bond only works when the sigma CH and the sigma star between carbon and bromine line up side to side. Otherwise, they can't mix. So the LUMO is only on beta protons that are anti to the leaving group. Your text has a special word for this. Your text will say that this proton is anti-periplanar with the bromine. And that's just a technical way of saying that the dihedral angle between these two in this Newman projection is 180 degrees. But that's exactly the same as saying that the LUMO is, that only beta protons that line up anti to the leaving group can have the LUMO on them. Yeah. I'm seeing the question from John. With the drawing, I'm only showing the LUMO spreading out onto one of the beta carbons. That, good point, John. That is for simplicity's sake. I just didn't want the drawing to be too complicated. The LUMO would spread out onto the other beta carbon or beta protons as well. Any beta protons that can line up with the sigma star will have LUMO on them. In this case, the molecule we've chosen, both of these carbons are identical by symmetry, but yeah, for completeness, we might have drawn the LUMO of this molecule like this, spread out into both areas. Okay, we're going to see examples later where only certain beta protons can get anti to the leaving group. And therefore, there are going to be some stereochemical consequences to the E2 reaction. What the heck am I talking about, E2 reaction? Well, a nucleophile looking at this alkyl halide starting material is going to have to ask, do I attack at the alpha carbon, in which case that's the SN2 pathway, or do I attack at the beta proton, and that's the E2 pathway. And this is going to lead to elimination versus substitution products. Again, as we did for the SN1 or for the E1 reaction, the SN2 reaction is pretty straightforward. You dump electron density into the LUMO at the alpha carbon, and that breaks the carbon-bromine sigma bond. What happens in the E2 reaction can be a little bit more challenging to see. So we're going to illustrate it out sort of in a step-by-step fashion by considering both the minus and plus combinations that we get from hyperconjugation. So again, I'm just going to show one of the adjacent carbon-hydrogen bonds that can be anti to our leaving group. We'll label things alpha and beta. Here's the other beta hydrogens. again, the LUMO is, I guess I'm just redrawing this to give you a little bit of time to catch up. Filling in the wave function signs, indicating areas of opposite signs so you can tell where the nodes are. All right. So this is a empty orbital that has that's derived from an antibonding orbital. So when a nucleophile / base attacks the beta hydrogen, you dump electrons into an antibonding orbital and the leaving group leaves. Where does the pi bond come from? Well, you can think of the pi bond coming from the plus combination. That's a terrible looking sigma. Plus combination, which would be something like this. It's not shown in the Spartan program, but if you did the calculations for what happens to those carbon-hydrogen bonds because of hyperconjugation, what you would get is something like this. The electrons in the carbon-hydrogen bond would be spread out a little bit towards the alpha carbon. And if you looked at it from a certain perspective, it would look like, again, we've got sort of a wannabe pi bond going on there, where the electrons in the carbon-hydrogen bond are already sort of leaning in that direction. So that as the nucleophile attacks and the proton gets removed and the carbon-bromine bond leaves, those electrons, and the bromine leaves with its electrons, these electrons in this plus combination just lean over and fully go form a pi bond. Again, we're not ever really beyond this point going to draw the mechanism out that way. I'm illustrating it so that you can have a sense for why the reaction happens the way it does. But in practice, when we draw the mechanism for an E2 reaction, we'll do it like this. Attack the proton, make the pi bond, leaving group leaves all at once. Yeah? Yeah. Yeah, this is a good question. There's a couple issues in there that I want to unpack and make sure I've got it all. The first point is that yes, there's another beta carbon here, and yes, those protons would be subject to attack as well. I just so happen to have chosen a starting material where it doesn't matter which of those you attack, they're the same by symmetry, and so you get the same products. The other question is, does the hyperconjugation from the nearby CH3 groups, does that contribute to the alpha carbon being less accessible because the LUMO is a little bit more spread out? And that sounds good to me. I don't know how important that is versus the steric repulsion due to those nearby beta carbons, but you could certainly think about it that way. One of the effects of hyperconjugation is to make the LUMO higher in energy, which would mean less accessible. So I suppose that's a reasonable explanation, but sterics works as well. Did I get the questions? Yeah? Okay. Yeah, so attack at the beta proton gives us the E2 reaction. And we'll talk maybe another time about the kinetics of the E2 reaction, but this reaction is concerted in the sense that we're breaking the carbon-hydrogen bond, we're making a new pi bond, and the leaving group's leaving all in the same step. Now, a couple of differences between, and we'll talk about this more, between the SN2 and the E2 reaction versus SN1 and E1. For the SN2 reaction, you can't do it with a tertiary alkyl halide. For the E2 reaction, it's just fine. Those beta protons are accessible no matter what the substitution pattern of the of the alkyl halide is. So we're not going to see that the rate of E2 slows down at all for tertiary alkyl halides. So there'll be some situations where you're stuck, you can't do SN2, but E2 is fast. There will be other situations where SN2 and E2 compete. And then there will be situations where SN2 dominates instead of E2. And we'll talk our way through all of that. Yeah, the double bond is there in the product because we removed the beta proton, the leaving group left, and the electrons from the carbon-hydrogen bond that were already sort of delocalized toward the alpha carbon move over completely to form a new pi bond. Wouldn't that leave only one CH3? Oh, you are right. Thank you, Richard at home. Yes, one of those would be a proton. I don't know why I made them methyls. That was weird. Sorry about that. All right. So we can now modify our horrendous energy diagram above with another line, and this is going to go, this sort of axis is going to go directly to the elimination products, and it's going to represent the nucleophile attacking the beta proton, making the new pi bond, and leaving group leaves all at the same time. The difference between what we're going to draw in orange and what we've drawn in pink is that for the pink pathway, leaving group left first. And so we've got a line in the background for the E2 reaction, maybe starting here. It's going to go through a transition state. I don't know how high in energy it will be. And in any case, I don't mean to communicate anything about the relative heights of the E1 versus the E2 transition states. I'm just going to try to clarify this a little bit. E1. What I mean to say is that E2 and SN2 compete sometimes. And as Jack Sparrow says, that's even less than maddeningly unhelpful. So we will talk about how to sort out what's going to happen. And that will depend on the alkyl halide and the nucleophile, because in both of these reactions, SN2 versus E2, the nucleophile and the alkyl halide are involved. So what we'll do is set up kind of a, well, we'll walk through what happens with each kind of alkyl halide when they're exposed to each of the 4 different kinds of nucleophiles / bases. But before we do that, let's pause for questions. I think I'm moving through this a little quicker than I did in the first hour, which may mean that I'm blowing through and not seeing questions or concerns. So, shoot. Nobody? All right, go ahead. Right. So we can talk about that. We've already said that for the primary alkyl halide, SN2 is fast. And it will turn out that E2 is slower for the primary alkyl halide. It's not impossible, but it's somewhat slower. And the reason has to do with the E2 transition state. So if you think about what's happening in the E2 reaction, and even look at the orbitals before the E2 reaction, as this reaction goes on, there starts to be a lot of double bond character here. And it will turn out that we're going to see more double bonds with more alkyl groups on them are more stable. And so the E2 transition state actually gets lower in energy for more substituted alkyl halides because the resulting alkenes have more groups on them as well. Now, we don't need to talk today about why alkenes with more alkyl groups on them are more stable, but for primary alkyl halides, we'll see that it's faster to go over the SN2 barrier than the E2 barrier. And that should make sense with a little bit when you think of elimination as coming from attacking a beta proton versus substitution coming from carbon, attacking at carbon. For the primary alkyl halide, attack at carbon is easier, whereas attack at the proton is about the same as it always was. And so the relative barrier heights change. That being said, the fact that for primary alkyl halides, SN2 wins and becomes the dominant thing, that may be a detail that you have to memorize, because there's not, other than what I've said, there's not a good reason why from first principles that should be the case. Yeah. Yeah, request from Isaac. Let's see hyperconjugation on the for the beta protons. Whoops. Yeah, so unfortunately I haven't got a pointer in Spartan, so I have to sort of rotate it around and tell you what I'm wanting you to look at. In the middle, where you've got the blue, the red, the blue and the red alternating from top to bottom, that is the sigma star. And then in red on those adjacent beta protons is that portion of the LUMO that has spread out because of hyperconjugation. And then if you actually turn off the orbital, you can see, if we look down a Newman projection, how the proton that had the LUMO on it is anti to the leaving group. All right. Yeah. The question here is, can E2 ever compete with SN1? The key way that SN2 and E2 compete with the leaving group leaving pathway is that good nucleophiles and or good bases aren't going to wait around for the leaving group to leave. So let me give you a couple of examples. If you have something that is a good nucleophile and a tertiary alkyl halide, good nucleophiles, let's say it's a good nucleophile but a weak base. A good nucleophile would normally prefer to do SN2, but it can't because it's a tertiary alkyl halide. It also can't do E2 because it's a weak base. So what do you have to do? You wait around until the leaving group leaves, and then you've got the SN1 plus E1 option. In contrast, if you have a good nucleophile that's also a good base and a tertiary alkyl halide, the good nucleophile would prefer to attack at carbon, but it can't because it's a tertiary alkyl halide. But our good nucleophile also is a good base, and so it's not going to wait around. It's going to go ahead and do E2. The times when we're going to wait around for the leaving group to leave will be when there are no other options available to us. Another example is secondary alkyl halide could do SN2, could do E2, but if you give it a weak nucleophile that's also a weak base, neither of those will prefer to attack directly. They will have to wait until leaving group leaves, and then you get SN1 and E1. So we'll walk our way through this based on the identity of the alkyl halide and the identity of the nucleophile or base. We'll be able to predict pretty well what the consequences of the reactions are. Yeah?
What would you define as a weak base? Is there a certain cutoff you should do?
Yeah, so what makes a weak base weak? Basically, sorry, I didn't intend that. It was an unintentional pun. A good base will have a conjugate acid with pKa greater than or equal to 16. So this is going to include hydroxide, various alkoxides, that is localized negative charges on oxygen. This will also include deprotonated alkynes. Their conjugate acids have pKa's that are around 25. So these will all of these are good bases that are also good nucleophiles. For things that are good bases but weak bases but good nucleophiles, you're looking at molecules whose conjugate acids have pKa's that are less than 16 but greater than 0. So these are going to be the ones that are not going to prefer to attack the beta proton first, but can attack the alpha carbon first. These will include, and there's a lot of things on a pKa table that would sort of satisfy this range. We've seen some of them already, and there are others, but basically these are, in many cases, lone pair electrons on a negatively charged atom whose conjugate acids are in this range. Things that are weak bases and also weak nucleophiles include molecules whose conjugate acids have pKa's that are less than 0. And this is basically water, methanol, ethanol, alcohol solvents. You've got, yes, lone pair electrons on the oxygen, but the oxygen is not negatively charged, so it's not particularly reactive. And so those categories sort of make sense. The last category is sterically hindered bases that are sterically hindered good bases that are weak nucleophiles because of the fact that they are sterically hindered. Remembering that it's tougher to get to an alpha carbon than it is to get to a beta proton. These are molecules that won't do SN2 chemistry, but are totally fine with doing E2 and won't sit around and wait for the leaving group to leave. And there are others, but I won't draw their structures now. So the good bases and the good nucleophiles, you're going to watch for SN2 plus E2 competition, depending on the alkyl halide. For weak bases but good nucleophiles, you're going to say no E2. It's either going to be SN2 or SN1 and E1, depending on the alkyl halide and whether or not, if it's tertiary alkyl halide, you can't attack. The weak bases that are weak nucleophiles, those are always going to be SN1 and E1. Or perhaps if you can't get the carbocation to form at all, then there'd be no reaction. And then the good bases that are sterically hindered is sort of going to be E2 only. Yeah?
Why would a moderately weak base, like, look at that second block, I would thought weak base and poor nucleophile would be synonymous.
Yeah.
I'm trying to wrap my head around why they prefer to attack a carbocation over the beta.
I guess I didn't mean attack the carbocation. I meant these will attack at the alpha carbon of an alkyl halide, but not at the beta proton. Why would that be the case? Well, I suppose it's just in terms of why they don't attack at the beta proton, it's probably just a pKa issue. right? Because attacking at the beta proton is just acid-base chemistry. So it's just they're not strong enough bases to remove that proton. But the fact that they're negatively charged means they're okay attacking the alpha carbon, because that's not necessarily a pKa issue. It's worth thinking about, and a lot of this is just based on our empirical observations. All right, that'll be enough for today. I will see you next time.